on the cloud. Okay. Yes. So I think what four of us are here usually. Oh, Michael, Rob, Jordan, I guess, and Khaled. Yeah. Okay. Okay. So, shall I help you with? I think probably number 5. The last part is what I gather is the challenge. I think so. I can give you broadly some hints. Okay.
For me, it was part D.
Part D.
Yeah, you gave us the hint where the difference of those two integrals was equal to
Yeah.
these other two integrals. I mean, for me, I thought it was due at 11 a.m. So I was going to work on it this morning, and then I woke up late and didn't. So I was like, oh man, I just need to submit it. So I didn't give myself the time to really work through that.
Yeah.
So I didn't solve. I basically just used the result of the hint, but I didn't actually do the mathematics too.
Yeah, sure. I can help with that also. Before I proceed, how many of you are taking qualifiers this weekend?
I do.
Leah?
I'm not.
Okay.
I will not be.
Okay. So because I'm going to postpone or not postpone, I'll give a possibility that the tomorrow's homework can be submitted within 1 week. Those who are not taking qualifiers, I think you should submit it. But some of you guys are, and I think since it's a department thing, I don't mind. But our homework will keep going, okay? That's my point.
We're still talking about the homework for EMT.
No, we are talking about this.
Now we're talking about math methods.
Tomorrow, yeah. Yeah, math.
Okay, so the math methods homework that's due tomorrow.
If you want, you can extend it. Okay. But I would say if you're not taking a qualifier, catch up with it.
Yeah.
Yeah, I also wanted to know how many people are taking the qualifier so that I know how much people get affected by that.
It's just PhD students, right?
Yes, PhD students.
Okay.
Yeah, although I just learned today that as a master's student, you can take the first time you take the qualifier is free. So you can take it at any point. So like I could, like if I wanted to, I mean, I don't feel prepared, but I could take the qualifier this time around just to see how I do. Is that correct?
I don't know actually. I will be giving something wrong information if I.
Okay.
Hey, Moses.
Yes.
But yes, it's if I want to be a PhD student. Yeah.
Yeah.
Hey, Moses. So when you say the first exam is free, do you mean the other exams are you have to pay for the exam?
I don't actually know about that.
No, you don't. That I can tell you. You don't pay for it, but there is a maximum number of attempts.
Number of times you can take it. Yeah.
Qualify.
Yeah.
So
this is what you were. So Professor suggests this is what you meant as free shot.
That's correct. Yeah. So this won't be counted against you if you by chance don't clear it.
Gotcha.
So if I gather correct, Luke, that means you are a master's student and not a PhD student. Is that
Correct.
what it is?
Yeah. Okay. But Michael probably has to take them. And Rob, but he's not in math methods.
Okay, so let me.
Wait, before.
Yeah.
Sorry.
Yeah. This is all free time. Yeah.
For the homework due in E&M Friday, I saw that like the second problem is like summarizing part of a paper, but I'm not sure if I can access that paper.
Oh, okay.
I've got it. I was able to access it. I just looked it up on Google Scholar, and I was at whatever journal it took me to. I was able to download the PDF. But if you want, I can email it to you.
Okay, that might be nice because
Sure.
it's the first place it looked.
Yeah.
Yeah,
Okay, sure.
inside the campus, it should be accessible. That's one hint. That's one
Okay. Yeah.
possibility.
Yeah.
If you access the site from the campus. Second is ask me. So I will get it. Like I
Okay.
have it, I think, downloaded, and I'll just send it to you. Or if Moses can send it to you.
I'll send it
Anyway,
to you now.
let that not be a hindrance.
Yeah.
And yeah, there are a few things going on in that first problem. Like whatever I did in the class is okay. It's just that the interpretation of that as to the pressure will be an issue. So in that sense, the same issues will go through in the homework also. But do whatever is there in the homework. So I realized today that there are various interpretations. If you do the volume integral, you're actually calculating something that is a certain pressure. And if you're doing the surface, that is something else. So that's why that factor of 5 showed up. So whatever we did may not be completely helpful, but just follow the steps. I think that's what I would say.
Sounds good.
And I plan to put a video on it, maybe just to clarify some doubts, maybe before Wednesday, maybe.
Okay.
Tomorrow is my big class where I have to do a few things for that. So that I cannot compromise. With you guys, I think I take some liberties. I can delay and all that. Yeah. Okay. Okay, so let's me help you with the homework. Anything else other than that? Any other comments?
Yes, I have.
Alia? Yeah.
It's the part E on the problem number 5. It's evaluate the angular momentum. I'm just kind of confused because there is some hint. But
sure. So how about this? I do D and E. Give hints for D and E.
Okay.
Okay. I don't mind that. Okay. And F you guys do. And before that, not just hints, I will give sufficient hints about that. Okay. So,
okay.
Is this visible? I don't use this too often. Okay. Let me know if it is not easily readable. Okay. So what was this? So we have phi E is equal to Q E over 4 pi epsilon naught times 1 over, I cannot read it. That's the electric potential due to a point charge, and electric field is equal to negative gradient of phi E, right? And that's equal to, comes out to be QE over And problem 1, I think yesterday, Moses, you were also asking. No, Jordan was asking, correct? And today again, Luke asked the same thing. If it is not clear where to begin with, just begin somewhere and don't make mistakes. That's all. Don't write wrong statements, but begin from wherever you want and get the Gauss's law if there is some issue with exactly what to do. My point was to begin from, I was also struggling with when you're designing a problem, you have to begin from somewhere. So I just said, get these equations using Gauss's law. It is, I can see a little vague, but don't give wrong statement. Like don't escape the problem completely, but do something which is reasonable in there.
Yep.
Is that good enough? Okay. So that clarifies that. That is, if you have a point charge, this is the electric potential, that's the electric field. There is a similar thing for magnetic charge. Everything remains the same, except this is mu naught. right? Is that, I think there is no big confusion in there. And we eventually want to keep the magnetic moment, magnetic monopole at the origin, and the electric charge on the z-axis. Okay. So that's what it is. And it turns out that we have to do an integral of the kind d cube x r dotted with, what is it? R dotted with, yeah, let me do the first one maybe. So R dotted with B, and then there is D. Right. So that's what it was. And I will do this. And the second one is pretty much goes this way, but there are slight small or very fine differences, but that could be your exercise. Right. So put mu naught and epsilon immediately, that comes out, and you have the cube r, let's say, d cube r, and this becomes, I'm going to use index notation. So this whole thing, this is a dot product, and this is your free index, right? So that's I. So this is j, rj times r. Maybe do this in 2 steps and if it is confusing. Okay, so this is r dotted with gradient is there. So there's gradient of phi, what do you call, phi m, right? And let me close that. And there's a negative of that, so that's a negative. And d, I replace it as just ei. Is that clear? I have not done anything in there, just put it. Now I want to use index.
Negative sign? Oh, you did. Never mind. You got it.
Is that clear?
Yes.
Okay. So that's minus epsilon naught, mu naught, as an integral. There is rj del j. It's just probably easier this way. And that is phi m. And this is ei. So that's a free index. That's your indices. That should be all clear. Now notice this is a derivative, and I'm going to do differentiation by parts. Okay. So, and think of, so del j phi m is one piece and rj ei is another piece. I can move things around now, right? There are no operators here. I'm going to move things around. Just the derivative, I have to be careful. Okay. So this is equal to minus epsilon naught, mu naught. So instead of this acting only on this, I make this a surface integral. So this is rj by m ei. That's obviously not the same as the other one. This is acting on all. This is acting on only one of them. So I have to subtract things out. Right. So to make this correct statement, I have to subtract, which is now addition, epsilon naught, mu naught. So you have to undo whatever extra I did here. So when it is phi m, it is of course the answer. So the rest of them I want to keep outside. So this is del j rj ei. Is that clear? Can I proceed?
Basic integration by parts, right?
Yes, basic integration by parts. This one, right, it is a surface, right, it has a, whatever is not, it goes on the other side, okay? we are integrating over the whole space because we are calculating the angular momentum of the whole space here. So this becomes a surface integral at the boundary of the universe. And we say that the electric and magnetic field goes off at 1 over r there, right? So this goes to 0, right? This doesn't contribute at the surface. Okay, so that's an argument you want to catch onto. So this is a boundary term. So this goes to 0. Is that clear what I said? This is a total divergence which will contribute using divergence theorem on the boundary. On the boundary, the electric field or the potential, either way, they are all dying off, and they should be dying off fast enough that they should go to 0. So argue that that is not real. That is really not there. Okay, that I'll leave it to you guys. You're the one has to argue that that's 0. So argue that, or deduce that. And what is left out is that, right? Now there are 2 pieces in there, so let me collect them. So it's epsilon naught d cube r phi m, and let me put them inside the bracket. So I can have del j rj times ei, and I can also hit on the second term. So this is rj. Oops, no, and this is del j. Okay. Which is, if I were to put this back into vector form, this is phi m. These 2 are dotted, so that's del dotted with r. That's the electric field. And this is plus vector r dotted with L. This is 3. Right, so that gives the expression for that. Okay. The second term is very similar, but what we are doing there is that instead of opening this, I will open that. Okay. Like I want to keep phi m, like because this will be the magnetic field. I want to keep the phi m outside. So maybe I'll write the first expression and then I will not do it. So this will be r dotted with d. And now this is b. Right. So this will be epsilon naught mu naught d cube r, and I do r dotted with e. And put a negative sign and have the gradient of phi m. Right. Actually, let me do this also because there is a small catch there. If you're not very much used to this, you might get stuck there. So let me do this also. But before I proceed, that is this very clear? Any questions on that? Because I'm going to erase that so that I need space. Okay.
Okay.
So this is 3. So this should be very clear. Yes. So we are done with that. And do the same thing here. Let me jump 1 step. I'll put j here, I here. 3. Index. Do integration by parts, and again argue that the surface term does not contribute. Okay, so there are a few steps you have to fill in the steps. Okay, so this is plus epsilon naught mu naught d cube r. Phi m stays outside, and this hits on this side. this is del I acting on Rj and Ej. Okay. And plus boundary term, Q1, which goes to 0. We try to argue that it goes to 0 because it's on the surface 1 over R. Now, this might seem that this is not really exactly the same as this. So let's do this slightly more. Epsilon naught, mu naught, EQR, phi of M, and write the two terms here. This is now del IRJ. Notice that's slightly different from this. This is now a dyadic, like I and a J coming in, that's a dyadic, so it's a unit dyadic. So that's great. And plus J del I EJ. Okay. Now, if you allow me to go cyclically above, you can put this here, EQX R dot D. So coming up, so this is equal to epsilon naught mu naught EQ R phi of M. This is del IJ, so that's pretty much 1 dotted with electric field. Hopefully that's clear. This one is 1 dotted with the electric field. So that's electric field itself, which is what has the answer. But this is not very obvious that this is the same as this. So here, if you notice what this is R. This is the free index. And this is the electric field. So this is dotted here. That's dotted there. That's not the same as this, this one here where these two are dotted. Where is that? No, this one, where these two are dotted. And that could be a confusion as to, oh, how do I proceed? But let's do this, go back to the index notation again. So this is Rj del I and Ej, right? Like dotted, and that's a free vector. So notice this is the same as this here. Put in the gradient. So this is Rj del I. Put it in the in terms of the potential. So that's J times phi of E. I temporarily do that. But now notice I can interchange these two. Right, because of the partial derivatives. And this is Rj del J and del I of phi of E. Very sneaky thing. It works out well, clearly. So this is, where did I do a minus? Yeah, and then put it back. So this is Rj del J EI. So it seems like this is the same as this, which is exactly the same as this. Not very obvious, but works out. I think since it's conservative force, that's how it works out. If you ever do this, yeah, we will encounter this in the next chapter again. So that should take care of. So this has all the Like if you go back and look into this video again, you should see everything is in there now. Okay, and this is electric field, of course. Okay, clear? Alia, out. Yeah.
That helped a lot. Thank you so much.
And this will show up again, so hopefully it will be useful. Like you guys struggling with this in the exam might be useful for the next week or so, hopefully. Okay, so so now we have to do the part E, right? So it seems like if you do all this, you get the angular momentum, L, right? That's apparently how much? I need the expression. Oops. QE, QM, and 2 pi, 4 pi. So this is QE, QM, 2 pi, 1 over 4 pi, and that is B cubed R of and that is 1 over yeah, and notice that the integration is on R, right? The integration is on R. Clear? And let me make that R prime, because at least in this class, try to integrate over sources and make that prime. That's okay, that's perfectly fine. Hopefully, it is clear that, remember, if you have 5 charges, electric field due to 5 charges is, how do you do this? You do a summation, right? Summation over Qi over 4 pi epsilon naught times 1 over R minus Ri square, and then vector, right? So R minus Ri. Right? No, Ri cube. Right, that's the electric field due to a point charge. If I want to get the total electric field, I'll just add them all together, right? So which is the same as saying if I were to do this for an integral charge density, then I do 1 over 4 pi epsilon naught and d cube R prime integral, and so instead of R i's, I have to integrate, right? So this is R minus R prime divided by R minus R prime, oh no, it's not magnitude, this is a vector, cube, and rho of R prime. That's, so this is not equal, this gets upgraded to that, correct? If you want, that's a superposition principle for electric charges, correct? Very straightforward. Any questions on that? Okay, so if we compare these two, it seems like, right? If it seems like, see, notice R here is observation point. And the rho of R prime is your sources. What are the charges if you want? So if I compare this with here, my observation point is actually RE in the problem. like if I want to do the analogy there. And my charge density is 1 over r prime minus rm. Right, that's my charge. If you want, I can try to plug in, like if, yeah, I can push this also in there, like with the factors. Okay, so but I will let you, yeah, that much you guys do. Take care of the factors, follow the factors. Okay, that can be an exercise for you guys. You guys take care of the factors. Okay, so that's what this is. And so I have to do this integral, correct? So, yeah, so I just have to do this integral for this configuration. But in problem 4, you do that using Gauss's law. So this is like saying you have a source at Rm, right? Rm is in the origin, right? So what we're talking about is that think of it doesn't have to be a magnetic charge, that is source at Rm. So keep it at the origin, right? And we are finding the electric field somewhere at a radius Re. Re, which is on the z-axis. So we want to find the electric field right at that point. Sorry, did I say this correct? No, I didn't say this correct because the charge, yeah, okay, so, sorry. I repeat, okay. So what is this? So this is charge density, remember, this is not a monopole sitting anywhere. This is the charge density, which is 1 over R. So let's have Rm 0 to begin with, okay? So actually for us, like in the problem, Rm is actually 0, right? So charge density is actually 1 over R prime, right? That's the charge density. So I asked the question, what is the electric field due to a charge density, which is 1 over R prime? Let's say some constant C. Constant C will involve all these things. But that's what we actually did in our problem 4. If you want to do that again, so we want to find the electric field, correct? So the total electric field. The electric field, we say that this is symmetric. This is symmetric configuration. So this will be E times 4 pi R square. Like this is Gauss's law. Electric field times the divergence of electric field. But you guys should do this more carefully. And this is equal to enclosed charge inside of that sphere. So this is d cube R. Right? So that's the charge density. So that's C over R prime. And that is 1 over epsilon naught, if you want. Right? That's Gauss's law. Like surface integral of the electric field is equal to this. And this is on a closed surface of radius Re. So sphere of radius Re, right? Because I want my observation point to be at Re. Okay. So that's the same as doing a spherical integral. So I say this will be 4 pi, no angular dependence over epsilon naught. And this is R prime square, R prime. And this is 0 to Re because it's a sphere of radius Re. And that's C over R prime. Right. And that will be equal to 4 pi over epsilon naught. C comes out, and that is Re over 2. Right, because that's a R prime square. Oh, R prime square over 2. So Re square over 2. Right, I think so. But the sphere radius is Re here. Re cancels. 4 pi cancels. So the electric field here is actually C over epsilon naught times 1/2. Right. And that's it, I suppose. And we have to put the direction also, right? This is the magnitude. The direction is in the radial direction of the sphere. So if I were to put the electric field direction, so there is an r hat here, which is assumed because we said that this is spherically symmetric. But the r hat in this case, this is the source, and the observation point is RE. Right? So my r hat will be equal to is RE minus RM divided by the magnitude of the sin. Right? Is that helpful? And if you put up all this together, you have part E. Like I went through a little sloppily in this Gauss law, but make sure you get all those details in there when you're put all the logical arguments in there. And once you have this, so basically the electric field is nothing but, we said this is the electric field, right? So we have got this integral. So this goes all the way there. Okay. So I think you guys should be able to put this all together now.
Yes.
Kind of a neat thing, yeah, that Dirac did this for the first time. I mean, it was not at all, no physical insight, right? Why should this be the case? And so it's considered a very remarkable result, actually. So, yeah. Any questions or comments?
No, thank you.
Okay. And I will post this in the, what do you call, in the playlist itself. You guys know how to reach the playlist. So if there is anyone else not knowing what to do, make sure you help them out. Okay. Right? They might try to contact me, but I may not check my email or I may not have access to stuff immediately. So because it's due learn. Yeah. Okay.
Okay.
Okay. And yeah, since I've told so much, yeah, feel free to 11 p.m. is not a hard deadline. How about that? Okay. Like hopefully we can have more exams and I'll get to do SS in some other place. So don't stress out with the exams. But for Moses, for you, this deadline holds because the moment we take away the deadline from you, you relax. No, I was just being hard on you.
Yeah, it's true. I'm doing it now, so I'll get it in for sure.
Don't worry. I was just saying, yeah, take it. don't postpone it.
Yeah, for
Okay.
sure.
Yeah. Okay. Anything else?
No, thank you so much.
Okay. Enjoy. Yeah. Okay. Take care.
Yep. Thanks.
Yeah.
Thank you.
Bye-bye. Yeah.
I have a question. So,
Yes.
if you want, you can stop the recording.
Is this going to be helpful for others?
Well, it's just my question, so I don't know if it's going to be helpful because you already talked about it.
Which problem is this?
5D.
Okay. Yeah. Go ahead.
You've already talked about it, so there's no need for recording. It's just my personal question.
Is it okay if I record, or do you want me to stop it?
I mean, well, the thing is, I got the non-surface term, and I just blatantly ignored the surface term and did not even write it when I solved for the problem. Is it okay?
No, just I mean, I noticed you have already submitted it, right?
Yes.
If you want, if it is not too much of an effort, just add that term and put in that this goes to 0, and
Okay.
I only see the latest file.
Okay, so the other thing is, I think, I don't know, like I did it the opposite way. So no, not this. So you said in number 4, we calculate the electric field using the integral, whatever integral that we did here. But the thing is, I did that integral in the fifth problem, and I used the idea from there in my 4th problem. Is it fine?
That should be okay. I mean, I won't see it, right? How will I know that how did you discover it? As far as it's there on both places. Yeah.
No, it's done in 5th problem, but it is not done in the 4th problem.
It should be done at both places, right? Don't you think so?
Yeah. Yeah. Well, if I'm editing,
I'm going to be lenient with this exam,
but
but
if
at
I'm,
the same time, I want the details in there. So lenient means that I may not take off too many points for something conceptual, but for example, I might get picky and say that, oh, where is the work? Right? I want the work. So yeah, if it's not too much of effort, just, I don't know what you mean. I haven't seen your work. So yeah, whatever you think is, I'll be lenient. How about it? Don't worry. Yeah. You're usually good with your work.
I mean, when using Gauss's law, so what I did was E times 2A is equal to surface time, that's sigma A over epsilon naught. So that's what I did for number 4, but I can change it if you want.
Let it stay. I will look into it. Okay. So if you think it's okay, let it stay.
Well,
I wouldn't ask you to repeat it, but don't come to me if I take away points. Okay.
Well,
I'm not promising points.
Well, if that's the case, I can spend a few minutes on it.
Yeah, I mean, you take the decision on that. Okay. Yeah. Okay.
I just don't want to be like, hey, this guy is uploading like 3 exams.
No, I don't see how many uploading you do, by the way.
Oh, you don't?
I only get the last one.
Oh, you don't even see how many I uploaded?
I don't even try. I have told it that don't give me that information.
Oh, I see.
Like I had that option, but I said.
Yeah, because I can see on my end that I've submitted 2 files.
Okay. As far as I know, I said I don't want the older ones. Yeah,
it's no big deal. I can just fix it.
Yeah. Like even if I want to, I think I cannot access the older ones. That is exactly for the reason that because I don't want students to come and say, oh, I had an older version, this and that. I said, no, I want only one version.
Okay.
Right. So that's why I chose to do that. So yeah, if that helps, if that information helps, do whatever.
Yeah, that's fair.
Yeah. Good. Yeah. Hopefully this was useful. Yeah.
Oh yeah, this was. I mean, I was not very sure about what I did. Now I'm sure.
Very good. Yeah. I think that's. I think sometimes what happens is that if students have worked on it themselves, then when I do it, then it's very clear what's going on. But in the classroom, that's not the case, right? You're seeing it for the first time. It's not very transparent. So hopefully this is useful, even though it was an exam problem. Like grading will go for a 6, but that's okay. Yeah. That's fine.
I mean, I don't get a grade, so.
Yeah. Oh yeah, that's true. Yeah.
So I just want to learn. That's it.
Good. Yeah, of course. I forget that you're not enrolled in this.
Yeah.
Okay, good. That's then I should be excusing everything for you. Yeah, don't worry. Yeah, don't worry. Yeah. I forget that. That you're not.
Yeah. So for number 3, I guess. So is the vector potential unique? Can I just say like A prime is A plus some gradient field, and any potential that satisfies this is the solution?
Yeah, that is there, but I want at least 2 concrete solutions. Do you see what I'm saying? I understand what you're saying. You're proving that it is not unique, correct?
So yes, I'm proving that it is not unique, and in addition to that, I'm saying any function that satisfies this is solution to this.
That's correct. Yeah, okay. Yeah, you're right. But I was expecting a concrete function. Give me a phi. You're giving an arbitrary phi. That's okay. I accept it. Fine. That's okay. Yeah, that's more than what I asked for.
Yeah, if you think it's fine, yeah. I think, yeah, this was helpful. Yeah, this session.
Good, 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 good.
I didn't have to worry about INJs like we had in our R dot gradient of E, R dot gradient of vector E. Yeah, I just have gradient and I can flip them.
R dot gradient of what?
So when we had R dot, the tensor product of gradient and E, vector electric field E. So I didn't have to worry about it because I just have gradient and I can just switch them.
Good, 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 good. Okay. Good.
This, I mean, I was just trying to do it vectorically without having to use the index notation. Yeah.
That's okay. That's
Yeah, I
perfectly
struggled
fine.
with it. Yeah, I spent like 15 minutes on it.
Yeah,
Finally figured it out.
sometimes index notation is a lot more faster if you want to say. Yeah, but that's okay. Any method is perfectly fine. I'll go through it. Like I try to avoid index notation in this course. Okay.
Yep, sounds good.
Okay. Take care, Avinash.
Thank you. Have a great day.
You too. Okay.